Welcome back to Calculus 1. In the previous lesson, we defined the derivative by taking the limit of a difference quotient. That process showed us why a derivative gives the slope of a tangent line and an instantaneous rate of change. In this lesson, we will turn that limit process into a set of differentiation rules. These rules will allow us to find derivatives much more efficiently. We will begin with constants and powers, extend the rules to sums and constant multiples, and then differentiate sine and cosine. Finally, we will use derivatives to describe velocity and other rates of change. So let's get started. Here's what we will cover in this lesson. First, we will differentiate constants and powers of the variable. We will then see how constant factors, sums, and differences are handled. Next, we will introduce the derivatives of sine and cosine. Finally, we will interpret a derivative as a rate of change with particular attention to position, velocity, and speed. In the last lesson, every derivative came from a limit. In this lesson, we replace the repeated limit calculations with rules that produce the same result in one step. We begin with two fundamental rules. The derivative of a constant is 0. A constant function never changes, so its graph is a horizontal line. Every tangent line is also horizontal and has slope 0. The power rule states that if f of x is equal to x to the power n, then f prime of x is equal to n times x to the power n minus 1, wherever the power function is differentiable. To apply the rule, bring the exponent down as a coefficient, and then subtract 1 from the exponent. The exponent may be positive, negative, or fractional. This means the same rule applies to ordinary powers, reciprocals, and roots once they are written in power form. These two rules replace the full difference quotient calculation for every constant and every power. Let's apply the power rule to three different forms. For f of x equals x to the power 7, bring the 7 down and reduce the exponent by 1. This gives f prime of x is equal to 7x to the power 6. For g of x is equal to the cube root of 3, first recognize that the cube root of x is equal to x to the power 1/3. Applying the rule gives g prime of x is equal to 1/3 x to the negative 2/3, which can be written as g prime of x is equal to 1 divided by 3 times the cube root of x squared. This derivative is undefined at x is equal to 0, where the graph has a vertical tangent. For y is equal to 1 over x to the power 5, rewrite the function as y equals x to the negative 5. The derivative is dy of dx is equal to negative 5x to the power negative 6, or dy dx is equal to negative 5 divided by x to the power 6. The main idea is to recognize roots and reciprocals as powers. Once the function is in power form, the power rule applies directly. Many functions need to be rewritten before the power rule can be used. In this example, y is equal to 3 divided by 4x squared. Separate the constant factor and rewrite the variable with a negative exponent. In other words, y is equal to 3/4 times x to the power negative 2. Now apply the power rule. The constant 3/4 remains in front, while the exponent negative 2 comes down and then decreases by 1. This will give us dy dx is equal to 3/4 times negative 2 times x to the power negative 3, which simplifies to dy dx is equal to 3 divided by 2x to the power 3. The original function and its derivatives are defined only for x not equal to 0. The pattern is this: rewrite, differentiate, and simplify. Rewriting is often the step that makes the rule visible. The constant multiple rule tells us that a constant factor remains unchanged when we differentiate. For y is equal to 6x to the power 5, the 6 stays in front, and the derivative of 5x to the power 5 is 5x to the power 4. Therefore, dy dx is equal to 30x to the power 4. For y is equal to 8 divided by x, we write the function as y is equal to 8 times x to the power negative 1. This gives dy dx is equal to negative 8 times x to the negative 2 to the power of negative 2, or dy dx is equal to negative 8 divided by x squared. The same reasoning applies when the constant is in the denominator. For f of t is equal to 3t squared divided by 7, the factor 37 remains unchanged, giving f prime of t is equal to 6t divided by 7. For y is equal to 5 times the square root of x, rewrite the square root of x as x to the power 1/2. The derivative is dy dx is equal to 5 divided by 2 times the square root of x for x greater than 0. At x is equal to 0, the graph has a vertical tangent, so there is no finite derivative. In every case, the constant comes along unchanged, while the power rule acts on the variable. The sum and difference rules allow us to differentiate one term at a time. For f of x is equal to 2x to the power 4 minus 7x plus 3, differentiate each term. The result is f prime of x is equal to 8 times x to the power 3 minus 7. The constant 3 contributes 0. The example on the right looks like a quotient, and we have not introduced the quotient rule yet. However, we can divide every term in the numerator by x. This rewrites y is equal to 4x squared plus x minus 6 divided by x as y is equal to 4x plus 1 minus 6 divided by x for x not equal to 0. Now differentiate term by term to obtain dy dx is equal to 4 plus 6 divided by x squared. The restriction x not equal to 0 remains because rewriting it does not restore the missing input from the original function. At this point, two basic functions remain, sine and cosine. The derivative of sine x is cosine x, and the derivative of cosine x is negative sine x. The graph helps us explain the first rule. As the sine curve moves from left to right, its slopes follow the pattern 1, 0, minus 1, 0, 1. Those values trace the cosine curve. The second rule includes a negative sign. That sign is essential and is one of the most common details to miss. Both rules assume that x is measured in radians. These simple derivative formulas do not hold in the same form when angles are measured in degrees. Now let's combine the trigonometric rules with the constant multiple, sum, and difference rules. For y equals 4 sine x, the 4 remains in front, and dy dx is equal to 4 cosine x. For y equals cosine x divided by 3, the factor 1/3 remains unchanged, and dy dx is equal to negative sine of x divided by 3. For y is equal to x squared plus 3 cosine x, differentiate term by term. The result is dy dx is equal to 2x minus 3 sine x. The positive cosine term produces a negative sine term. For y equals 2 sine x minus 5 cosine x, the derivative is dy dx is equal to 2 cosine x plus 5 sine x. Subtracting cosine creates a positive sine term because the derivative of cosine already contains a negative sign. The functions have changed, but constants and sums are handled exactly the way they were with powers. Now it's your turn. Differentiate each of the 4 functions using the rules from this lesson. Work term by term and rewrite roots, reciprocals, or quotients before differentiating whenever necessary. Pay close attention to negative exponents and to the negative sign in the derivative of cosine. Pause the video now and work all 4 problems. Then continue when you are ready to check your answers. Let's check the answers. For problem 1, f prime of x is equal to 15x squared minus 4x. Differentiate term by term, and remember that the constant 9 contributes 0. For problem 2, rewrite y is equal to 10 divided by x cubed as y equals 10x to the minus 3. The derivative is dy dx is equal to negative 30x to the power negative 4, or dy dx is equal to negative 30 divided by x to the power 4. For problem 3, divide each term in the numerator by x. The function becomes y equals x squared plus 4, but the original restriction, x cannot equal 0, remains. Therefore, dy dx equals 2x for x not equal to 0. For problem 4, dy dx is equal to 3 cosine x minus sine x. The sine term becomes cosine, and the cosine term becomes negative sine. Rewriting is not extra work. In many problems, it is a step that makes differentiation possible with the rules we currently have. We now shift from finding derivative formulas to interpret what a derivative means. A derivative measures the rate at which one quantity changes with respect to another. If s of t gives the position of an object at time t, then v of t equals s prime of t. This gives us its instantaneous velocity. Average velocity over an interval is s of b minus s of a divided by b minus a. Geometrically, this is the slope of a secant line between 2 points on the position graph. As the time interval shrinks, the secant slopes approach the tangent slope. The tangent slope is the velocity at one instant. For vertical motion, we define upward as a positive direction and downward as the negative direction. Therefore, positive velocity indicates upward motion, while negative velocity indicates downward motion. Velocity includes direction. Speed does not. Speed equals the absolute value of velocity, so speed is never negative. Consider a ball dropped from a height of 144 feet, with position s of t equal to negative 16t squared plus 144. We will compare average velocities over intervals that all begin at t equal to 2, but have right endpoints that move closer to 2. From t equals 2 to t equals 3, the height changes from 80 feet to 0 feet. The average velocity is negative 80 feet per second. From t equals 2 to t equals 2.5, the height changes from 80 feet to 44 feet. The average velocity is negative 72 feet per second. From t equals 2 to t equals 2.1, the height changes from 80 feet to 73.44 feet. The average velocity is negative 65.6 feet per second. As the interval shrinks, these average velocities approach negative 64 feet per second. Differentiating the position gives v of t is equal to negative 32t. Therefore, v of 2 is equal to negative 64 feet per second, confirming the value approached by the secant slopes. The negative sign indicates the ball is moving downward. The general position model for an object moving vertically near Earth's surface is s of t is equal to negative 16t squared plus v0t plus s0 when distance is measured in feet. The constant s0 is the starting height. At t equals 0, the other terms equal 0, so s of 0 is equal to s0. The coefficient v0 is the starting velocity. A positive value means the object begins by moving upward, while a negative value means it begins by moving downward. The coefficient negative 16 comes from gravity. Near Earth's surface, gravitational acceleration is approximately negative 32 feet per second squared, and the position formula contains 1/2 of that value. In metric units, the corresponding coefficient is approximately negative 4.9. This model assumes that air resistance is ignored. From one problem to another, negative 16 remains fixed, while v0 and s0 describe the object's initial motion and height. Let's look at an example. A swimmer leaves a platform 24 feet above the water with an upward velocity of 8 feet per second. The position function is s of t is equal to negative 16 t squared plus 8t plus 24. To find when the swimmer reaches the water, set s of t equal to 0. Factoring gives the solutions t equals negative 1 and t equals 1.5. Negative time is not relevant here, so the swimmer enters the water after 1.5 seconds. Next, differentiate the position function. The velocity function is v of t is equal to negative 32t plus 8. At impact, v of 1.5 equals negative 40 feet per second. The swimmer is moving downward, and the speed is 40 feet per second. At the highest point, the vertical velocity is 0. Solving v of t equal to 0 gives t equals 0.25 seconds. Substituting this time into the position function gives s of 0.25 equal to 25 feet. The position graph rises briefly, reaches its maximum height, and then falls until the swimmer enters the water. Now it's your turn. Use s of t equals negative 16t squared plus 64 to answer 3 questions about a falling stone that begins 64 feet above the water. First, determine when the stone reaches the water. Next, find its instantaneous velocity at that time. Finally, calculate its average velocity over the entire fall. Remember that average velocity requires a time interval, while instantaneous velocity is found at one specific time. Pause the video now and work all 3 problems. Then continue when you are ready to check your answers. Let's check the answers. For problem 1, set s of t equal to 0. This gives t squared equals 4, so t equals plus or minus 2. We discard the negative solution, and the stone reaches the water after 2 seconds. For problem 2, differentiate the position function to obtain v of t equals negative 32. Therefore, v of 2 equals negative 64 feet per second. The negative sign indicates downward motion, and the speed is 64 feet per second. For problem 3, use the complete interval from t equals 0 to t equals 2. The average velocity is s of 2 minus s of 0 divided by 2 minus 0, which is equal to 0 minus 64 divided by 2, which is negative 32 feet per second. Because the acceleration is constant and the stone starts from rest, the average velocity over the entire fall is 1/2 of the impact velocity. The instantaneous velocity is a tangent slope, while the average velocity is a secant slope. Both describe motion, but they are not the same quantity. Let's bring the main ideas together. The derivative of a constant is 0. The power rule brings the exponent down as a coefficient and then reduces it by 1. Constant factors remain unchanged, and sums and differences are differentiated one term at a time. The derivative of sine x is cosine x, and the derivative of cosine x is negative sine x, provided the angle is measured in radians. Rewriting a function as powers or as separate terms is often the first and most important step. A derivative also represents an instantaneous rate of change. For a position function, the derivative is velocity. Average velocity is a secant slope, while velocity at 1 instant is a tangent slope. In the next lesson, we will extend these ideas with the product and quotient rules for functions formed by multiplication and division. Thank you for watching. In this lesson, we used the basic differentiation rules to differentiate constants, powers, sums, differences, sine, and cosine. We also connected derivatives with rates of change and used position functions to distinguish average velocity, instantaneous velocity, and speed. In the next lesson, we will introduce the product and quotient rules. I'll see you there.